class. Today we're going to be looking at section 5.4, finishing up some things from 5.5, and just looking at some final integration topics that didn't really fit in some of the previous lectures. I guess they could have, but not necessarily the main focus. Okay, the first thing I want to talk about is the continuity requirement for the fundamental theorem of calculus. So recall that the fundamental theorem of calculus requires continuity of the integrand f of x on, say, the interval a to b. Okay. And I want to show why this is and what happens when, say, you look at something that's not continuous and what you end up getting. Okay, so let's take a look at that. Alright, so to start, let's consider this definite integral here, the definite integral from -1 to 1 of 1 over x squared dx. First thing I will notice is that 1 over x squared is even. So since this guy is even, and I tend to just write even underneath the equal sign just so it's clear to everybody what I'm doing here. But since that function is even, this is going to be basically 2 times the integral from 0 to 1, right? And at the same time, I'm going to change this guy to x to the -2. All right, then I'm going to do this. That's 2 times this integral will be -x to the -1, and I'm going to evaluate that from 0 to 1. Okay. So this ends up being 2 times -1 plus 0 when it's all said and done. Okay, so this ends up being -2. All right. So this is what you would get using the fundamental theorem of calculus, right? So here, this is the FTC coming in the picture here. But here's the problem. Okay, the problem is that 1 over x squared is not continuous on -1 to 1. Okay, if you were to look at the graph of 1 over x squared, it looks like this. Okay, and actually a bit steeper in here, but this is good enough. So this is what 1 over x squared looks like. Here's 1, -1. This is 1. Okay, and using the fundamental theorem of calculus, we found that the area between the graph and the x-axis should be -2, which doesn't actually make any sense, does it? Because one, this entire region is above the x-axis, right? But even if it was positive, this area right here, we have a 2 by 1 rectangle. This area is 2, and then we have all this up here. In fact, this guy shoots up to infinity on both sides at 0. So one would think that we have, well, an area of 2, and then this infinite region going up forever. How does one determine what that area would be? Would it be infinite? It's quite possible. So basically, the fundamental theorem of calculus fails here. Right? So don't use the fundamental theorem of calculus on situations where your function is not continuous. Okay, so the FTC fails here since 1 over x squared is not continuous on -1 to 1. Right? It's discontinuous at 0. Now the question from here is, well, can we say maybe use limits or something to find the area of this? Maybe break this integral up from -1 to 0 and 0 to 1, or just look at the integral from 0 to 1? And the answer is yes. We can deal with discontinuous functions and areas, but the answer to that, you won't really see that until Cal 2. All right, so we approach this, or studied, in Cal 2. Okay, but it's essentially you split it up, you use limits, and what you know about limits. You could probably, figure it out if you're resourceful on your own. Okay, so that's the first thing I wanted to really talk about today, was the fact that the fundamental theorem of calculus does not always work. You are required to have continuity, and when you apply it to something that's not continuous, you get something funky. Okay? All right, next thing. Okay, 5.4 is mainly about symmetry, which we've actually done already. Right, we've talked a lot about symmetry. That's even and odd rules. Okay, so I'm not going to focus too much on that. You've seen that already. Your worksheet for this particular day might end up having some problems that ask you to use symmetry, but it's one of those things where even if you don't know symmetry or they use the symmetry rule, you can usually find the definite integral, without it. But the other thing 5.4 talks about is the average value. Okay, and so essentially the average value of f of x over the interval a to b is simply, it's basically just 1 over b minus a times the integral from a to b of f of x dx. Okay, so basically the average, if you want to take the average of something over b minus a, or on a to b, it's over an interval, you have the function. You can do that by basically just integrating and dividing it by b minus a, or multiplying by 1 over b minus a. Okay, and I'd like to give an explanation of where this comes from, because this may not seem all that basic, right? It may not make much sense to you, so I will give an explanation. Alright, so let's say there's my function here, f of x. I want to take the average of f, values of f over the interval a to b. So what I'm going to start with, I'm going to start by splitting the interval up into n subintervals. Okay, so I'm going to have x's going from x sub 0 all the way up to x sub n, and I'm going to, add or take the average of all these values. Okay, so the average, of course, is going to be f of x sub 1 plus f of x sub 2 plus f of x plus x sub 3, all the way up to f of x sub n. And what do you do to take an average of n items? Well, of course, you divide by n. Right? And what we're essentially going to do is, let's say we want, so that's the average over n subintervals, but what if I want to average all the values of f? Okay, so let's say we wish to average all the values of f. On a to b. Well, if we would like to do that, essentially what we're going to do is take the limit as n goes to infinity of this average of n elements. Okay, because when we do that, and this is equal subintervals, but as the number n increases without bound, the length of each one, delta x we'll call, is going to go to 0. So we'll basically be averaging up every single point. Once, as n reaches infinity, we get closer and closer to actually averaging up every single value of f. Okay, so I'll write that down. Okay, so the question, of course, was, say we wish to average all the values of f on a to b. To do so, we let n go to infinity. Okay, so the average value of f on a to b is the limit as n goes to infinity. And I'm going to write this guy with the sum notation we talked about before, that sigma notation, right? It's sigma. Actually, I'll write it once over here. Right, we're going from 1 to n. Okay, is going from 1 to n. All right, of f of x sub k divided by n. Okay, so we are looking at the limit of that thing. So the limit as n goes to infinity of the sum, k ranging from 1 to n, of f of x sub k divided by n. Okay. Now this should look very familiar. This looks almost like an integral, right? The definite integral came from this infinite limit. And the reason I'm going through this is because anytime you sum up a bunch of stuff, say you want to split up your interval into n pieces, and you want those pieces to go to infinity, you're probably going to ending up with an integral at the end. And you'll see explanations like this throughout Cal 2, specifically where the physics applications come from. Okay? And that will lead you to an integral. So anyway, we almost have an integral, right? So what I'm going to do is, if you go back here, your delta x, remember we have a step size that's equal, so equal step sizes. And if you remember how we got delta x previously, it's b minus a divided by n. Okay, so this is also, you could write that delta x is 1 over n times b minus a. All right, and we have a 1 over n here. Right? So basically 1 over n, if I divide this, delta x over b minus a is 1 over n. Right? So what I end up with here is, I'm going to rewrite it like this, k going from 1 to infinity, okay, of f of x sub k times delta x over b minus a. And here's the trick, as n goes to infinity, this thing goes to 0. So as n goes to infinity, delta x goes to 0, making it a dx for our purposes. Okay, so what we really have here, all right, and actually let me rewrite this with the limit right now, just so I can make this step more clear. Right, I still have the n's. When I bring the infinities in, then I'll call it a dx. Okay, so this is dx over b minus a. And I'm going to factor the b minus a out. This is 1 over b minus a times the integral from a to b, f of x dx. Okay. So actually, let me go ahead and leave this as a delta x. It doesn't really matter, but that's how we get the average value. Okay, that's really where it comes from, is we are just summing up all of the values of f and then dividing it by how many values that is. So basically we're adding up an infinite number of f's and dividing it by infinity, essentially. All right, and when you're asked to find the average value, it's basically this simple. Okay, so let's look at a couple examples, but honestly, it's just calculating an integral. You're just going to multiply it by 1 over b minus a. Okay, that's essentially all. Okay, so if we want to find the average value of 1 over x squared on 1 to 3, okay, essentially this is just going to be the definite integral from 1 to 3 of 1 over x squared dx, and I'm going to take that and multiply it by 1 over b minus a. Okay, so this is just going to be 1/2 the integral from 1 to 3 x to the negative 2 dx. Okay, and from here it essentially follows like normal. It'll be 1/2 times, I'm going to integrate, so it'll be negative x to the negative 1. I'm going to evaluate this from 1 to 3. So this will be 1/2 times negative, remember this is negative 1 over x, so this is going to be 1/3 minus a negative 1. Okay, so this ends up being 1/2 times, this is negative 1/3 plus 1, so this is positive 2/3. So we get 1/3. All right, so the average value of 1 over x squared on the interval 1 to 3 is simply 1/3. And that's it. Okay, let's do another example. Okay, let's find the average value of sine on 0 to pi. Okay, so essentially it's just the integral from 0 to pi, sine theta d theta, except you multiply by 1 over pi minus 0. So this will be 1 over pi. Okay. So this will be 1 pi. Then we integrate. So the integral of sine is negative cosine theta. And I'm just going to evaluate this from pi to 0. So this will be 1 over pi times negative cosine pi plus cosine 0, right? Because we're subtracting, but since it's a negative, you know, you get it. Okay, so cosine of pi is negative 1, cosine of 0 is 1, so this is 1 over pi times 1 plus 1. So this is 2 over pi. Right, and that's that. I mean, it's not, you know, I don't want to spend too much time on this because it's not something that pops up a whole lot in this class. You may have a problem on the final. I've seen it before, but again, it's just something you should see at least once, because later on down the line, and maybe engineering class or something, you might need to use this. Okay. Now, what I really want to spend some time talking about is continuing our discussion of 5.5, right, our use substitution on the problems that are a little more difficult to deal with. Okay, so some problems that are a little harder. So, for example, okay, so I'm going to call this 5.5 star. Okay, say I want to integrate, right, x over x minus 3 dx. Okay. Now, this is not, there are a lot of problems here because this is not a typical rule that we know. We don't have a backwards quotient rule. Okay. And we can't use algebra like we do before. I mean, if this was the integral of x minus 3 over x, this would be no problem because you would just split this up and get 1 minus 3 over x dx, and you could move on from there. Very simple. The problem is we can't do that here. And you might think, oh, well, let's do u substitution. Right? And that is the answer, but there's a little more work involved. Right? Because usually you would say, all right, I'm going to let u be the denominator. And that means du is going to be simply dx when we take the derivative. Ah, but we have an extra x. Everyone see that? We don't have just dx, we have x dx. So in cases where this happens, right, in special cases like this, where you have x in the denominator, and numerator, all right, you're basically going to translate u's on the top and the bottom. Okay, so the idea is to translate u's on the top and bottom. Right, and here's how. I have that u is x minus 3, so the denominator I know is just simply u. Okay? But the numerator, right? The numerator is simply x. All right? Now I can't just replace this with u, but I could replace it with u plus 3, because what happens if I took this and move that 3 over, you end up with u plus 3 is equal to x. So the numerator is actually u plus 3. Okay? So what I end up with is the integral of u plus 3, because that's what x is, over u, because that's what x minus 3 is, du, because that's what dx is simply du. Okay? And now I've rewritten it so where this can actually be split up as u over u plus 3 over u du. Okay? Which is, of course, 1 plus 3 over u du. So the integral of u, the integral of 1 is simply u. The integral of 3 over u is 3 ln absolute value of u plus c. And then you just put your x's back in, right? X was x minus 3, so this is going to be x minus 3 plus 3 times ln of x minus 3 plus c. Okay? So these tend to happen when you have basically basically you have the inner functions on the top and the bottom. So you have, say, a degree 1 polynomial here and a degree 1 polynomial there. Okay, so say you might have an x squared would be your u. Okay, and well, sorry, not x squared, but like an x plus 1 would be your u, but you have like an x minus 5 and somewhere else. So it's not the form of the derivative, but it's the form of u. Okay, it usually only shows up in cases like this, barring a couple of others. So let's this is what I really want to focus on here, because these can be kind of complicated. So I want to kind of give you a few examples of how you approach it. Okay, and it's usually linear functions that you'll see, but not always, so be careful. All right, so more examples. All right, let's look at this next example. Let's say I have the integral of x over the square root of x minus 2. All right, so here's a case where my inner function is x minus 2, and its derivative isn't sitting on the top, but a form of it, like a linear combination of it, is sitting there. So, so what we're going to do is we're going to let u be that inner function. So we still do that. We take that inner function, and we let u be that, x minus 2. Okay, and then here we have x. So we're going to solve for x in this case. And that's typically what you do. So you get u plus 2 is equal to x. Okay, and then du, of course, is dx. Whoops. All right. So what we essentially have here is that this is u underneath the square root. Jeez. Okay. So we have that u here is underneath the square root. This x becomes u plus 2. Okay. Then this dx becomes du. All right. So when we translate this, this becomes the integral of u plus 2 over the square root of u, which is, I'll just go ahead and write, is the square root of u, du. All right. And now, as is going to typically be the case with these problems, we are going to split up the fraction. Shoot, sorry about that. Okay. So, here we go. I get u over u to the 1/2 plus 2 over u to the 1/2 to start with. So I did two things here. I split it up and I rewrote this square root as u to the 1/2. That's going to help us. Then what we get is, okay, the integral of, this is u to the 1 minus 1/2. And I'm writing it now for those who don't remember, but you definitely should by this point. If you don't know how to do this kind of stuff by now, you're kind of in trouble. All right. So this is the integral of u to the 1/2 plus 2u to the negative 1/2 du. And this we know how to deal with, right? This is u to the 3/2 when we integrate times 2/3, okay, plus 2 times, this will be u to the 1/2 times 2. And we're finished. Okay, so now we just put our x's back in. So u was x minus 2. So this will simply be 2/3 times x minus 2 to the 3/2 plus 4 times x minus 2 to the 1/2 plus c. All right, and that is our answer. So remember, you basically just take u to be the denominator thing still, or that inner function still, and then you solve for x, essentially. Okay? So let's look at a more difficult example. Okay? Alright, so here's our next example here. Let's say I have the square root of x plus 2. Oh, sorry. The integral of x plus 2 times the square root of 2x plus 3. So that inner function is still 2x plus 3. Okay, so I'm going to let u be 2x plus 3. And so du is going to be 2 dx. Alright, so the first thing is I don't have a 2 dx. Well, you might think I do, kind of here, but I don't really. Okay, so first thing I'll do is 1/2 du is equal to dx, so I know that this guy is going to be u, this guy is going to be 1/2 du, okay, and then now I need to worry about this x plus 2. So to deal with that, right, what we're going to do is solve this thing for x. Okay, it's as simple as that. So essentially, I have that u minus 3 is equal to 2x. And if I divide both sides by 2, I get that 1/2 u minus 3/2 is equal to x. Right, and here's what x is. This thing, 1/2 u minus 3/2. So x, I'm going to replace by 1/2 u minus 3/2. Okay, I'm going to leave that plus 2 sitting there. That's going to mess with this thing, but you'll see. So when I basically do my translation, this x becomes 1/2 u minus 3/2. I still have that plus 2, so constants don't really get messed with for the most part, times the square root of just u here, okay, times 1/2 du. Now whenever I have a 1/2 du, I typically just move that all the way out to the front to begin with. So this will be 1/2 times the integral of, this is 1/2 u. Alright, now I have minus 3/2 plus 2. This is 4/2, so this will be 1/2 plus 1/2, then times the square root of u du. Okay, I'll stop for a second there, just to catch your breath. Okay. Now, this guy here, they both share 1/2, so I can actually factor out a 1/2 again. So I'll go ahead and do that. I will now get 1/4 times the integral of u plus 1 times, and now I'm going to rewrite this as u to the 1/2 du. Okay. All right. Now, what I will end up with is I'm going to distribute this thing because we don't really have a backwards product rule yet. Right? So I'm going to distribute this u to the 1/2. So before it was splitting up the fraction, but you won't always have a fraction. Sometimes you'll be multiplying. So here we'll be distributing that u to the 1/2. So I get 1/4 times the integral u times u to the 1/2. So that's u to the 1 times u to the 1/2. Okay, so that will be u to the 3/2 plus u to the 1/2 du. Okay, so we get 1/4 times this whole thing. So this is going to be u to the 5/2 when I add 1, then times 2/5. Okay, plus now this will be u to the 3/2 times 2/3 plus c. Notice the plus c shows up the minute the integral sign disappears. Okay, and well, we could sorry. What we're going to do now, we could go ahead and put the x's in if we want. Sorry about that. Okay, but what I'm going to do is distribute this 1/4 now, just to make it a little simpler. 1/4, so 1/4 with these 2's, essentially it cancels and leaves a 2 in the denominator. So I'm going to end up with a 1/10. Now I'm going to put the x back in. So if you remember, u was 2x plus 3, so this will be 1/10 2x plus 3 to the 5/2 plus, now this is going to be 1/6 times 2x plus 3 to the 3/2 plus c. Okay. And that is that. This gets a little complicated as you see, but essentially if you just have a linear guy here, and your u sub doesn't get rid of another x that's sitting around there, just solve for it. Solve x in terms of u and then replace those extra x's with u's. Okay? Alright, next example. Let's say I have the integral, you can see that, of x times the cubed root of 2x plus 1, or sorry, 4x plus 1. Okay, so once again, I'm going to let this guy be u. So u is equal to 4x plus 1, giving me that du is 4 dx. Okay, now again, I have just dx, so this will be 1/4 du is equal to dx. Beautiful. Okay, so this dx will be replaced with the 1/4 du. Now this x, of course, I need to solve. So I'm going to subtract by 1, so u minus 1 is 4x, and once again, dividing by 4, I get 1/4 u minus 1/4 is equal to x. So that is what is going to go right here. Okay, so I'll write that in. This piece is going to be 1/4 u minus 1/4. Alright, so this will now be the integral of 1/4 u minus 1/4 times the cubed root of u, and then that 1/4 du, I'll go ahead and take that 1/4 out like that. Okay. And then I also have this extra 1/4 that I can factor out, so I'm going to get 1/16 times the integral of, this will be u minus 1 times u to the 1/3 du. Okay, and once again, I'm going to distribute. Okay. And once I do that, I will now have, 1/16 times the integral of u to the 1 times u to the 1/3. That will be u to the 4/3. Okay, minus u to the 1/3 du. And now we can just use the backwards power rule. Give me 1/16. Shift this up a little bit. 1/16 times. All right, so when we add 1 here, we're going to get u to the 7/3. So this will be 3 times 7, or sorry, 3 over 7, minus u to the 4/3 over 3/4. And of course, plus c. All right, now that 3 is not really going to play nicely with the 16. Okay, so we could just leave it like this if we wanted. We could also distribute that 1/16, but we're not going to get very nice things in the denominator there. We could move that 3 out and have it just factored when we put our x's back in, and that's what I'm going to do. I'm going to have 3/16. Then this will be 1/7 times, and I'm going to put my x's back in. So remember, u was 4x plus 1, so this will be 4x plus 1 to the 7/3 minus 1/4 times 4x plus 1 to the 4/3. The whole thing plus c. And there we go. Okay. All right, the next example I want to look at, and this one's kind of more complicated. This is the case where we have two inner functions, right? We have two inner functions. All right, because we have x squared, but x, I mean, as an inner function, that's not all too bad. And then we also have x plus 2 raised to the 4th. All right, now the how you pick what you want your u to be, I hate to just say always go for the denominator, but in this case, we're going to go for the denominator. And it's basically because we can't do anything with this. We could expand this, but it wouldn't do anything. Now, if you've noticed that when we expand stuff, or sorry, when we use u as the denominator, it changes the numerator, so it expands. So we can actually expand something squared pretty easily. So that's what we're going to do. We're going to let u be the denominator. Okay. Well, I should say not the full denominator, but this inner function in here, x plus 2. All right. So that makes du simply dx. So that's a straight translation there. Dx will become du. And then to get this, well, this is x squared. So let's solve for x like we usually do. Here it's simply u minus 2 is equal to x. Right? And what I'm going to do is I'm going to squeeze some parentheses around here, and my x is going to be replaced with u minus 2. Right, basically, u minus 2 all squared will be x squared. So I'm going to replace x squared with u minus 2 squared. Okay, so what I end up with, all right, is u minus 2 squared. Oh, didn't mean to do that, but it doesn't matter. U minus 2 squared all over, okay, this is u to the 4th du. Okay, now what does this do for us? Well, if I expand this out now, I could do u minus 2 all squared, right? That will be u squared minus 4u plus 4. And this is all over u to the 4th. And now I can actually break this fraction up and actually integrate this. So I have u squared over u to the 4th minus 4u over u to the 4th plus 4 over u to the 4th du. Which most of you would probably just skip to this step. This is 1 over u squared minus 4 over u cubed plus 4 over u to the 4th, which you will in turn make these powers, right? This is u to the negative 2 minus 4u to the negative 3 plus 4u to the negative 4 du. And now it's just a matter of using the backwards power rule. Okay, sorry about that. So this is going to be negative u to the negative 1 minus, right, this will be 4 times u to the negative 2 over negative 2, okay, plus 4 times u to the negative 3 over negative 3 plus c. And I'm going to simplify this quite a bit before I start plugging x's back in. This will be minus 1 over u. This will end up being plus 2 because the negatives and the 2 it cancels. So this will be, let's make this 2 over u squared. All right, can move that down. Plus, and actually, sorry, that's minus 4/3 u to the negative 3, so I could put u cubed in the denominator like that. Okay. And then we're going to put our x's back in. So our x's, if you remember, well, u was x plus 2. So x plus 2 is going to be put into our u's. So I'm going to get negative 1 over x plus 2 plus 2 over x plus 2 squared minus 4 over 3 times x plus 2 cubed plus c. All right, so yeah, there are definitely some cases where some people can get by without using u substitution on some of the standard problems, but there are definitely cases like this. We're looking at this original problem, x squared over x plus 2 to the 4th. I do not immediately see this. Okay? And so for cases like that, u substitution is completely invaluable. I mean, probably the only method we could use here to actually get this answer out. Okay? Since I can't look at that and just think backwards and get to an answer. Okay? So, hopefully this is a glimpse of the fact that integration is not always as easy as it seems to be early on. You probably thought derivatives were pretty easy until you got to the chain rule. Well, same thing here. Integrals are pretty easy until you get to u substitution, and then they get even worse when you get into Cal 2. Anyway, that is all I pretty much want to talk to you all about. That kind of finishes up all the loose strings regarding integration. Anyway, I hope you have enjoyed it, and hopefully, for those of you who remember everything, I will see some of you in Cal 2. All right, cheers.